Hello, everyone, and welcome to Lecture 10. Today, we're going to talk about memory, and in specific, we're going to talk about two memory technologies. The first one is SRAM, or Static Random Access Memory, and the second one is DRAM, or Dynamic Random Access Memory. Okay, so let's get started. Last time we began to introduce sequential logic, which is we're still in part one of the course, and specifically we looked at some fundamental building blocks of sequential logic, namely latches and flip-flops, and we also looked at how to build registers in a register file, which is one type of memory. So we said sequential logic is a type of logic where the output of a logic block may depend on the input as well as some values stored in the block. And we usually in sequential logic we use edge-triggered clocking, where there's this notion of an active edge. So clocks they oscillate up and down. So there's a rising edge and a falling edge, and usually one of these edges is considered, it could be either updates to the state element. Logic usually happens on the active edge. Said that a state element is kind of a component in a circuit whose content gets updated on the active edge. And typically when we build sequential logic, we usually have state elements and some combination logic between them, where at the beginning of during the cycle, the combination logic will operate on kind of some value from some state element to produce a new value, and this new value will be written to another state element, or as we'll see later, perhaps the same state element at the end of the cycle on the active edge. We said to do that, we need to be able to build circuits that are able to store data. And we started doing that by building what we call an SR latch. So an SR latch is a circuit like this, where we have two NOR gates. Each NOR gate has an input S or R, but then also the other input to each of the NOR gates is the output of the other NOR gate. And we saw how by connecting these NOR gates in this way, by connecting the output of one to the input of the other and having this kind of loop in our circuit, what we've done is we've created a circuit that has the ability to store data. And we saw how when we set S and R to 0, we will simply hold on to the old values of Q. But then when we set SR to 0, 1, we will set Q to 0. When we set R to 1, 0, we will set Q to 1. And we said that we don't care about the last state. We then built on the SR latch, where we wanted to have a situation where we could have one input to control whether or not we write or we hold, and another input to control what value we want to write. And to do that, we built a D latch. So a D latch adds these two AND gates as the inputs of the SR latch. And with the D latch, we have an input C, where when C is 0, we hold, and when C is 1, we update. And in the case where C is 1 and we're updating, the value that gets updated is the value D that we give as another input to the D latch. Next, what we did is, we said that, okay, now we have a circuit that updates when C is 0 and updates when C is 1 and holds when C is 0. But what we actually wanted is a circuit that would hold throughout the entire clock cycle and only update on the active edge. So to build that, we connected two D latches together. And we used C as the input to one and not C as the input to the other. And by doing that, what we've done is we've built a circuit, which is the circuit that we want, and that's called a flip-flop, where we hold throughout the entire duration of the clock period and update on the active edge. And the way that is done is by providing these two different latches with opposite clocks. What happens is when C is 1, one of them updates and the other holds, and then when C is 0, the opposite happens. The first one will hold and the second one will update. And we have an example of how that works. Someone has a question?
Yes, I didn't get the use of D flip-flop.
Oh, well, the use of a D flip-flop, what a D flip-flop does is it holds a value for the entire duration of a clock cycle and updates it on the active edge, meaning at the end of that clock cycle. So that's what a D flip-flop does. Is your question about what it does or how it works?
About what it does.
Okay, so what it does is exactly what I just said. It holds a value throughout the entire clock cycle and updates it at the end of the clock cycle. And we're going to look at all kinds of use cases of a D flip-flop, where a D flip-flop is useful. In fact, we started looking last time at one of the use cases of flip-flop, which is building registers. So registers were arrays of D flip-flops where these where if we want to store an n bit value, we use n different D flip-flops, and together they form a register that can store n bits. And we provide the same clock to all of these D flip-flops so that we have a register. And we saw how we can use registers to build a register file. So a register file is one of the applications, one of the usages of D flip-flops,
Well,
where we build a register file. So a register
what
file.
just a second. What I didn't understand last lecture is that okay, so if it stays only for one clock cycle, then it doesn't work for the register because the register can store for more than one clock cycle, right?
So I may want to change the value of a register every clock cycle, or I may want to for multiple clock cycles. If I want to keep the value for multiple clock cycles, what I can simply do is have kind of the clock, and we saw this later on in last lecture, where we guard the clock with another AND gate that has another signal. Where we have set that signal to 0, it prevents the clock from reaching the register. And in that case, what happens is that that value will stay there for multiple clock cycles.
Won't it become zero because nothing is passing?
Back to that slide, okay? I'm about to review that slide, okay? A few minutes, I'll get to that slide, and then ask me again when I reach that slide. That way I can explain it to you on the right slide. Okay, so we said that a register file is a that contains multiple registers, and what we would like to be able to do with a register file is, or specifically the register file that we're building, we want to be able on the same clock cycle to read two different pieces of data and also write one piece of data. So maybe I want to read register 5 and register 6 and also write to register 7 on one clock cycle, and we can do exactly that. That we provide two register numbers and get the data that's stored in these registers, and we also provide a register number to store to and the data that we to that register, and specify here whether or not we would like to write. Okay, and we saw how to have support for reading from the register file. We simply have a bunch of registers, and the register numbers are used as select signals for the multiplexers. So here, if I want to be able to read two different pieces of data at the same time, I can simply have two multiplexers with two different select signals, and this allows me to read two different registers. And if I would like to write to the register file, here I'm going to provide the number for the register I'm writing to, the data that I would like to write, and also a signal that says whether or not I want to write, because it may be the case that I don't want to write to any registers on that clock cycle. So here what we did is we had these registers, and in order for us, of course, we passed the data that we want to write to all the registers, but we may want to write to only one register, or maybe want to write to none of the registers. So what we did is, rather than passing the clock directly to these registers, we passed the clock to an AND gate, and the AND gate included two other signals. The first signal is a write signal, and this write signal over here specifies whether or not we would like to write on the cycle. If we don't want to write to any of the registers on the cycle, what happens is we set this write signal to 0. So the input, one of the inputs to all these AND gates will be 0, which means the output of all these AND gates will be 0, which means that none of these registers will get modified on that cycle. And I hope that that answers your question. The other signal besides the clock that we passed in is an output of the decoder. So we only want to write to one of these registers on any clock cycle, and that's the write register number that we provided. So what we do is we decode the write register number. When we decode it, if this, for example, was register 1, what's going to happen is the value for register 1 here will be 1, and all the others will be 0, which means this AND gate will Okay, we just lost connection, so we're back now. And we left off talking about the writing to the register file. And we saw how by combining the clock, the write signal, and the output of the decoder, we can choose to write to the register that we want, only one of the registers, the one that we want, and also we choose to write only if the write signal is 0. Is this clear to everyone, how we write to registers? And is it clear how we combine these signals to only write to one of the registers? And if we want the register to keep its value for multiple cycles, we simply don't let the clock pass in by disabling the write signal and not selecting that register. Is it clear to everyone? Any questions?
Yes, I have two questions, Professor. First, here we are only able to write one bit at a time, right?
So remember, each of these registers is an n-bit value. Okay, so each of these registers is n D flip-flops. So if I'm building a 32-bit register file, each of these registers are going to be 32 D flip-flops, so 32 bits. So we will write 32 bits at a time, but we will only write to one register at a time.
Okay, so my second question is irrelevant.
Okay.
Sir, I have a question about the decoder, I think. At the clock, actually. Would it be one for all the registers? So if I pass a clock, would it be one for all the Cs?
No, so here what's going to happen if I pass the clock, these AND gates will prevent the clock from being 1 for everything. The clocks will be 0 for all the registers except one register, which is selected by the decoder, or none of the registers if the write is set to 0. Okay?
So the clock would just have what
It'll just be
bytes?
0 the whole time.
Oh, okay. Thank you.
Okay, and if it's 0 the whole time, the registers will never get modified. They will only get modified if we have an active edge.
All right, thank you.
Yeah, you're welcome. Any other questions? All right, well, if there are no questions, then let's get started with today's material. So again, today we're going to talk about SRAM and DRAM.
So,
Yeah, does someone have a question?
I have a quick question, yeah. The D flip-flops we learned about, are they meant to be used specifically when the active edge is the falling edge, or can they be used also when the active edge is the rising edge on the clock?
Okay, so the specific D flip-flops that I showed, the active edge for those is the falling edge. But if you just, switch where you put the inverter, you can get a D flip-flop where the active edge is the rising edge.
Yeah, okay. Thank you.
Yeah, you're welcome. Okay. Remember, we spoke briefly before about memory. We said a memory is kind of a storage, is a logic block that stores data, where if we provide it with an address, it gives us the data stored at the address, and we can also provide it with some data we want to write in an address and a write signal, and it stores data at that address. And at that point, I told you that different technologies for building memories will be covered later, and now is later. So today, what we're going to do is we're going to talk about different technologies for building memories. So different types of memory. A register file is a type of memory, right? So we've already talked about register files. We've already talked about a type of memory that allows us to store data, read data, and write data at specific addresses. Some of the kind of the features of the register file that we have built are as follows. First, we can read 2 registers and write 1 register every clock cycle. So the specific register file that we built allowed us to read 2 registers and write 1 register every clock cycle. And this is a very nice feature of register files, the fact that you can read and write the same register on the same clock cycle. The second thing is we can read and write to the same register on the same cycle. The reason we can read and write on the same register on the same cycle is because a value is held for the entire duration of the clock cycle and updated at the end of the clock cycle. So if I want to read from register 5 and write to register 5 at the same cycle, the value of register 5 will be held the entire cycle, so I'll be able to read it during that cycle. And then at the end of that cycle, it will be written. So I can provide register 5, for example, as both the read and the write register, and it works. And then finally, another feature of register files is that they typically have a small number of registers. And the register file we're going to be dealing with in this course it has 32 registers. Okay, which is it's a decent number, it's a good number, but it's a relatively small number compared to all the memory that we have in the system, for example. The next type of memory we're going to talk about today is a static random access memory, or SRAM. And SRAM is going to have higher capacity than register files, right? Because it's not enough to just have a register file in your system. We need to be able to store data than 32 registers, where a register is typically 32 bits. Okay, so what we want to do is we're going to build something called SRAM, and SRAM is going to have higher capacity than register files. Okay, so SRAMs are going to be larger and denser. By larger, I mean they can store more data, and by denser, I mean they can store the same amount of data using less hardware. Okay, the same amount of data using less hardware. That's why they're more dense, because in the same amount of area, the hardware area, I can store more data. Now, of course, this doesn't come for free, right? Having higher capacity for an SRAM to have higher capacity than a register file, it does not come for free. Obviously, there's something that we have to sacrifice in order for us to get larger and to be larger and denser. And the trade-offs are as follows. First, we're going to have slower access latency than register access than a register file. Going to be either read or write during a clock cycle. We cannot do both. Okay, or we're going to write. We're not going to do both. And it turns out that by preventing SRAM from being by not supporting the ability to read and write on the same clock cycle to the same location, this gives us the ability to use less hardware to build the SRAM. Okay, so let's look at how we're going to build SRAM. So first of all, we said that registers may be read and written on the same cycle in a register file. And what this means is that the register will have to be held the entire cycle and only updated on the active edge. And for this reason, we needed to use flip-flops to be able to guarantee that a value will not be written during the clock cycle, because it needs to be read throughout that clock cycle. So in contrast, with SRAM, we're going to allow either to read or to write a location on the same cycle. We're not going to allow both, okay? And what this means is that we can update a value during a clock cycle. We're not restricted to only updating it on the active edge, okay? Because the reason we needed to hold it for the entire clock cycle is because the value we're about to write might be currently being read by someone. But if we say that, okay, if I'm going to write to a value on this clock cycle, nobody's allowed to read it during that clock cycle, that means is I don't need to wait for the active edge to write it. I can write to that location during that clock cycle. Okay, so if the output is being written, then it's not being read, which means it does not need to be held for the entire clock cycle. Now, what does that mean? That means that I can actually use a latch. I don't need to use a flip-flop. So remember, with latches got written to when C was 1, and they hold their value when C was 0. Okay, and what we did is we put 2 latches together to get a flip-flop, so that we only write at the end of the cycle. So with SRAM, because I don't allow the reading and writing on the same cycle, right? I can write during the clock cycle, not just on the active edge. So it's sufficient for me to use a latch instead of a flip-flop. And that's exactly what we're going to do with SRAM. We're going to use latches instead of flip-flops to build SRAM. Okay, so the other difference between register files and SRAM is that register files typically have a small number of registers. So for example, the register files we're going to use, they have 32 registers, which means that when we read from the register file, we need a 32-to-1 multiplexer to select the right register to read. Okay, we need a 32-to-1 multiplexer to select which register we want. Now for SRAMs usually store large numbers of entries. So an SRAM could have 2 million entries, for example. Okay, that's much larger than just having 32 registers. And because SRAMs are much larger than register files, building a 2 million to 1 multiplexer is infeasible. Okay, remember how we built multiplexers? We needed to have these AND gates and this OR gate at the end. So imagine an OR gate with 2 million inputs. This is something that's very large and that cannot it's not feasible to build. So what we're going to do is we need to have a different technique in order for us to select the entry that we are going to read. Okay. So these are the 2 distinctions between SRAM and register files. Now let's see how we're going to do the selection for SRAM. And to see that, I'm going to introduce a new kind of device, which is called a 3-state buffer. So a 3-state buffer is a circuit whose output can be in one of 3 states. So before we were looking at circuits where the output can only be in one of 2 states, 0 or 1. So a 3-state buffer can actually have 3 states. One state is low voltage, which is 0. Another state is high voltage, which is 1. And then the third state is called high impedance, and we represent that as Z. And what high impedance means is that for practical purpose, the circuit is going to function as an open circuit. It's not going to conduct electricity. Okay, electricity. So a 3-state buffer looks like this. It has an input, it has an output, and it has an enable signal. And the truth table for a 3-state buffer looks like this. If enable is set to 0, the 3-state buffer will function as an open circuit, so there will be nothing here at the output, and we represent that as Z, meaning high impedance. And if enable is set to 1, then this 3-state buffer will act as a wire that conducts electricity. So if my input was a 0, my output will be a 0, and if my input was a 1, my output will be a 1. Okay? So a 3-state buffer has 3 states, 0 or 1 or high impedance. Now, why is this useful? Well, it's useful because we can use 3-state buffer to perform selection when the number of inputs is really high. So for example, if I want to use 3-state buffers for selection, what I can do is I can take all these inputs that I want to select from, okay, and I can connect them all to 3-state buffers and connect these 3-state buffers to a single wire. Okay, I'm going to connect these 3-state buffers to a single wire. Okay, and then if I want to select one of these inputs, let's say I want to select input 1, then all I have to do is I have to set enable for this 3-state buffer to 1, and I set the enable for all the remaining 3-state buffers to 0. Now, when I do that, what happens is this 3-state buffer over here is going to act as a wire, so it's going to conduct. But all these 3-state buffers are just going to be open circuit. So I just connect them all to a wire. Only one of these will be connected in practice, and all the others will be open circuits, so they won't affect the result on this wire. So previously, when I built a multiplexer, what I did is I had a bunch of AND gates feeding an OR gate. Now I have a bunch of 3-state buffers connected to a wire. Okay.
Sir, I have a question. In the last slide, when you went over the 3-state buffer and like the control inputs, could you go over that table one more time? Because I was kind of confused.
Okay. So here, the way a 3-state buffer works, it has 2 inputs, a regular input and an enable signal. When the enable signal is 0, it's just going to be an open circuit. And when the enable signal is 1, it's going to act as a wire. So it's going to forward the input to the output. So here, when the enable signal is 0, we're going to have Z, which means high impedance, which means we have an open circuit. And when the enable signal is 1, it means the output is going to be equal to the input. So it's going to act as a wire. Okay?
Okay.
Is it clear now?
Yeah, I get it now.
Okay. As we put all these inputs to 3-state buffers, connected these 3-state buffers to a wire, and now if we want to select one of these inputs, what we do is we're going to use a decoder. We pass the select signal to the decoder. The decoder, based on the select signal, will set one of these outputs to 1 and all the others to 0. Therefore, one of these 3-state buffers will be enabled and all the others will be open circuit. And therefore, this wire over here is only going to take a value from one of these 3-state buffers to become the output. Okay?
Sir?
Yes?
Don't we have the same problem as before? The decoder has to be 2 million output long?
Yes, that's a very good observation. We do have the same problem as before. It's a slightly smaller problem because before, when we had a multiplexer, the multiplexer had a decoder, but also had an AND gate for each one of these, which is more expensive than a 3-state buffer, and also had an OR gate that was taking inputs from all these AND gates. Okay, so we need to have this huge OR gate, which is not feasible. So now we've solved the problem of the OR gate and the AND gates, but we still have a very large decoder. And in practice, what we do is we kind of break down the SRAM into multiple smaller SRAMs, and then select the result from these different SRAMs. So it's as if we broke down our decoder into multiple decoding stages. Okay, but we're not going to get into that in this course, but that is a very good observation, that we still have a very large decoder, and we solve that problem by breaking the decoder into multiple stages.
Basically, it becomes as if we were organizing things into tables, right?
I mean, there's different ways to think about it. You know, that's a valid way to think about it if you want. No, not multiple threads. Threads has nothing to do with this. We have different stages of decoding. If you're interested in how we break decoding into multiple stages, feel free to ask me during office hours, but I don't want to get into it today because we don't have time for it. Okay, so having done this, now we know how to use 3-state buffers for selection. Now we can build an SRAM. So this is how we're going to implement an SRAM. First, what we're going to do, okay, before that, let me talk about what the SRAM is. So an N by M SRAM is an SRAM that has N entries, which are M bits each. So if an SRAM has N entries, it's going to have an address that's log 2 of N. Okay, it's going to have an output that's M bits long. It's also going to have a data in that's also M bits if we want to write, and it's going to have a write signal. So if I set write here to 0, remember, I'm either going to write or I'm going to read. I'm not going to do both on the same clock cycle. So if I set write to 0, that means I want to read, so which means I'm going to take the address over here, and I'm going to read the value at this address to data out. And if I set the write to 1, that means I want to write. I'm not reading. So what I'm going to do is I'm going to take this address over here. I'm going to write this data over here to that address. Okay, so this address is going to be both the read and the write address, depending on whether this signal is read or write. And again, I cannot read or write on the same cycle. Okay, so the key points about implementing an SRAM compared to implementing a register file: we're going to use latches as our 1-bit storage elements instead of flip-flops, because we're either going to read or write. We're not going to do both. I keep repeating this because it's a very important point. And then finally, and then again, we're going to use 3-state buffers to select which entry to read, as opposed to using a multiplexer. Okay, so let's build an SRAM. We're going to use latches as storage elements. So an SRAM is just going to be an array of latches. Okay, we're going to have rows of latches, and we're going to have columns of latches. Now you can think of each row of latches as being one entry in the SRAM. Okay, and what we would like to do is, depending on the address that we have, we're going to select one of these rows to read from or to write to. Okay. For each column of latches, we're going to have a bunch of 3-state buffers connected to a wire. Okay, same thing for this column, same thing for this column. And we're also going to have a decoder that is going to, activate the, each output of the decoder is going to go to one row of latches and activate that corresponding 3-state buffer. So what happens here is, let's say I want to read from address 1. What I do is I'm going to activate this line over here. This is going to be set to 1. All these others are going to be set to 0. What that means is these 3-state buffers on this row are all going to become wires. They're going to conduct. All the other 3-state buffers in the other rows are going to be open circuits, meaning they're not going to conduct. And by doing this, what I'm going to do is, in this case, what I would do is I would be reading the data in these 3-state buffers. Sorry, in this row of latches over here. Okay, is it clear how we read from an SRAM? Any questions? All right, well, let's look at writing to SRAMs now. Okay, someone asked me to repeat. So when I want to read to the SRAM, what I do is I provide the address I want to read from. So if this address was 1, I'm going to activate this line over here. This line here will have 1, and all the other lines will have 0. And what that means is that the 3-state buffers in row 1 are all going to conduct, whereas the 3-state buffers in all the other rows are going to be open circuits. So the values stored in the latches in row 1 will be read along these wires to the output down here, whereas all the other rows will just have open circuits, so these values will not be read. Okay, clear? All right, now if I want to write to my SRAM, what I'm going to do is I'm going to pass the data that I want to write over here. So so if I have an m bits of data, then I'm going to pass the data down to these columns. Okay, but I only want to write to one of these rows. I don't want to write to all these rows. So again, what's going to happen is I'm going to pass in a clock, of course. I'm going to pass in the clock, but I'm going to only pass this clock to the place that I want to write, if I want to write. So what I'm going to do is going to have a write signal, and this write signal is going to also go as an input to the AND gates. And I'm also going to pass the decoder value, the value from the decoder, to the AND gate. Okay, so now what happens is, if I'm writing, I'm going to set the write signal to 1. So these AND gates will all have 1 from the write signal. The clock is ticking, so these AND gates are all getting the clock. However, the decoder will only set one of these bits to 1 and all the others to 0. So if I want to write to address 1, what happens is this AND gate will have a 1 for the decoder. It'll have 1 for write, and the clock will pass through. So these latches will get written to. whereas all the other rows will have 0 from the decoder, so the clock will not pass through and the other rows will not get written to. Okay?
Professor?
Yes, question?
Here we can write and read and write at the same time.
So theoretically, right, it's possible to read and write at the same time, but the problem here is if I try to read and write at the same time, what's going to happen is I'm setting if I set my write signal to 1, the value inside of the latch is going to change in the middle of the clock cycle, right? The value in the latch is going to change as soon as the clock is 1. It will not be held for the entire duration of the clock cycle. And what that means is if someone tries to read at the same time that I'm writing, the value that they read will be something in one part of the clock cycle and something else in another part of the clock cycle. Okay? So the value that they're going to read is not going to be reliable because I am changing that value in the middle of the clock cycle. So that is what I mean by we cannot read and write on the same clock cycle, because if we are writing on that clock cycle, the value that we are reading is not going to be reliable. So we shouldn't try and read it. Okay, clear now?
Sir, I have a question.
Yep.
Yeah, so does this mean that SRAM will read or write faster than the register file if it doesn't need to wait for the clock cycle to finish?
So no, it will not read or write faster, and the reason is that we have a much bigger decoder here. So if you have a bigger decoder, it means the decoder is going to be slower.
Oh, okay.
Okay, so there's multiple aspects that go into the speed of reading and writing. Okay, one of them is the decoder, and that is why SRAM is actually slower to read and write than register files, because they're much larger. Okay, even if we are able to read, write, but we have more time to write because we can write during the clock cycle, not just on the active edge. So in an SRAM, we have more time to write, and we need that time because we have a bigger decoder.
Okay. Thank you.
That's what I mean by SRAM is slower to read and write than register file. Okay. Any other questions?
Sir, so
Yes.
when we're reading and we pass in an address, we pass that address in and it reads the value from the queue of the row of D latches, right? And it goes to the output. So
Yes, exactly. Exactly. When we pass an address coded, if the address is 1, the line for 1 will be set to 1. So these 3 state buffers in row 1 will conduct, the others will be open circuits, and here at the output we're going to get the values from row 1.
And when we're reading, say we pass an address to read, write is always set to 0, right? So that signal will never come out of the AND gate at the same time as we're reading.
Yes, correct. So here, if write is set to 0, that means we are reading. If write is set to 1, that means we are writing.
Okay, so because it can never both be 0 and 1 at the same time, then they're like exclusive.
That's correct. Whereas in the register file, if you remember, we had the ability to both read and write. Okay, so if we set write to if we set write to 1, right, we would be writing, but that doesn't mean we're not reading. We would also be reading. But here in the SRAM, if we set write to 1, that means we're writing. That means we're not reading. Okay.
Yeah. Okay.
Okay, great. So we are done talking about SRAM. Next, I'm going to move on to the next topic, which is DRAM. So another type of memory is dynamic random access memory, or DRAM. And DRAM, for DRAM, we can also either read or write on a cycle. We can't do both. So this is like SRAM and unlike the register file. However, DRAM has higher capacity than SRAM, right? So we said that SRAM has higher capacity than register files because SRAM uses latches, whereas register files use flip-flops. DRAM is going to have even higher capacity than SRAM, so they're going to be low. They're going to store more data, and they're also going to be denser, meaning they need less space to store a value. And of course, this comes at a cost. So we're not going to be able to make DRAMs larger and denser for free. There's a trade-off here. And the trade-off for making DRAM have higher capacity than SRAM is, first, DRAM is going to be slower to access than SRAM. And second, DRAM is going to be dynamic, hence the name dynamic. And what dynamic means is that data in DRAM is going to fade away with time and needs to be refreshed, which means that if I store data in SRAM, that data stays there as long as the power is on. Okay, as long as my computer's plugged in, the data in SRAM stays there. However, the data in DRAM, in dynamic random access memory, if I have the power plugged in, that does not mean the data will stay there. If I don't want to lose my data, I need to constantly refresh that data, and we'll see how this happens. Okay. So DRAM is going to be higher capacity than SRAM, but it's going to be slower to access, and data fades away with time, so we need to constantly refresh it. All right, let's see how we can. So with SRAM, our storage unit for SRAM consisted of a D latch, right, and a 3-state buffer. And you can remember that a D latch, there were multiple gates that went into building a D latch. So a D latch consists of many transistors. It takes many transistors to build a D latch. So you have a D latch and a 3-state buffer. This was what we needed to store 1 bit of SRAM. On the other hand, with DRAM, all we need is a single capacitor, right? So rather than having all these transistors to build a D latch, what we're going to do is we're going to have just one capacitor to store the 1 bit of storage in DRAM. And obviously, one capacitor is going to take much less area than all the transistors that we need to build a D latch. Okay. All right, great. So what we're going to do is we're going to have a capacitor, and for those of you who are familiar with capacitors, we can if we can charge up capacitors, right? We apply charge to them, and they kind of remember that charge as long as the circuit remains open. So if the capacitor is charged, this is going to correspond to a 1, and if the capacitor is not charged, this is going to correspond to a 0. Okay, if the capacitor is charged, that's a 1. If the capacitor is not charged, that's a 0. Okay, so this is great. The advantage of this is we have higher density because capacitors need less area than a latch. We have one capacitor versus many transistors, but obviously there's a disadvantage, and let's see what that is. So the disadvantage is we have something called destructive reads. So let's say I wanted to read from a DRAM. What I'm going to have is I'm going to have all these DRAM cells, and they're all going to be connected. They're going to be guarded by a 3-state buffer, and all these 3-state buffers will be connected to a single wire. And if I want to read from one of these DRAM cells, I'm going to activate the corresponding 3-state buffer. So let's say I want to read from this capacitor over here, this DRAM cell. I'm going to enable this 3-state buffer. So this will become a wire, and all these others will become an open circuit. And when I enable this 3-state buffer, what's going to happen is this capacitor is going to discharge. So if I have if I have a 0 on this capacitor, it's not going to discharge. And down here, I'm going to have something that senses, oh, this capacitor did not discharge, meaning it has a 0. Okay. However, if I have a 1 in this capacitor, what's going to happen is it's going to discharge, right? And when it discharges, I'm going to detect down here that the capacitor that I have a 1. But when I read the value in the capacitor, when the capacitor discharged, what happened? I changed the value, right? If I had a 1 over here, right, the capacitor discharges to tell me that I have a 1, but when the capacitor discharges to tell me that I have a 1, it no longer has that 1. So by reading the value, I've destroyed it. Okay, by reading this value, I've destroyed it. So the solution for this is I'm going to have a latch down here, right? So rather than having a latch for every single cell, I'm going to have one latch for the entire column. And what I'm going to do is when the capacitor discharges, it gives me a 1. I'm going to store this 1 in the latch. Okay. And then after I store this 1 in the latch, I'm going to go and write it back to the capacitor. Okay, so if the capacitor discharges and writes the value to the latch is going to then come back and write the value back to the capacitor, which means every time I read from DRAM, I'm discharging the capacitor, so I need to go back and write that value back. So now every read is going to be both a read and then also a write back. And you can obviously see why this is a disadvantage. The disadvantage is that we have slower read latency, because every time we read, we also need to write back, and this write back slows us down. Okay, clear? Is it clear why DRAM is denser, gives us higher capacity, but it's also slower?
Sir, can you explain why we have a column latch? What's the purpose of it again?
Right. So when we read from a capacitor, we lose the value. It discharges. Okay. So we want to be able to read this value, store it in a place where we can remember it, and then write it back. Okay. So the column latch will, in a latch, when you store a value in a latch, it stays there. Okay. It doesn't get destroyed when you read it. Okay. So whereas when you store a value in a capacitor, it gets destroyed. So we're gonna read from the capacitor to write to the column latch, and what this does is it destroys the value in the capacitor. It stays in the column latch, and then we're gonna read from the column latch and write back to the capacitor. But because this is a latch, when we read from the column latch to write back to the capacitor, we don't destroy the value in the column latch, so we can still read it later on to use it.
Oh, so you have values like old Q and old Q complement?
Yes, it's a latch. It works like the latches we've seen before.
All right, thank you.
Professor?
Yes?
With those, how do you call it? The two bars, the take that discharges. How do you make sure that the voltage that you have is right, or that it keeps like a 1? Because you don't know that it's going to stay a 1.
So why do you think we don't know that's going to stay 1? So if the capacitor is charged, that means it's a 1. If it's discharged, that means it's a 0.
Well, to register a value, it needs to have a constant 1. But when it discharges from a 1, then it goes down to 0.5 and then down to 0. You see what I mean? It's not a constant 1.
Right, and that is why when I read from from DRAM, I need to write the value back so that it stays 1.
Oh, okay, I see.
Okay, so that's exactly the point. Because we destroy the value when we read it, we need to write it back, and that's what makes things slower. Okay. All right, there's one more thing I mentioned, and that's the word dynamic. And another problem with DRAM is we have something called leakage. Okay, so we said that if I read from this capacitor, the value goes away and you need to write it back. But there's a bigger problem, which is even if I don't read from the capacitor, the value still goes away. That's because of leakage. So these capacitors, they're very small and they leak. And what that means is, these electrons that are stored in this capacitor will eventually kind of jump over, and they'll kind of jump over the edges of the capacitor, right? So with time, what happens is these capacitors leak and they lose their charge even if we don't read them. And for this reason, what we have to do is to deal with this leakage issue is that we need to periodically refresh the data by reading it and writing it back. Okay, so even if I never read this value over here, if I never use it, what DRAM has to do is that to prevent losing data due to leakage, it periodically has to go and read all the data and then write it back in order to kind of refresh the value. And this is what I meant by the data fades away with time and it needs to be rewritten. It fades away because of this leakage on these capacitors. And typically a DRAM spends 1 to 2% of the time just doing refresh operations. So 1 to 2% of the time, the DRAM module in your computer is not reading or writing to give you data. It's reading and writing just to refresh the data to make sure it doesn't get lost. Okay. And obviously the disadvantage here is that we have even slower access latency because these refresh operations interfere with the normal read and write operations, so they slow you down. Okay, so that's all for today. You can refer to section B.9 if you would like to read more about SRAMs and DRAMs. Does anybody have any questions?
Is it the same technology today that's being used, or is it more complex?
So loosely speaking, it's the same technology. Obviously, there's a lot of advanced techniques and optimizations that are used, to optimizing these things. But the purpose of this course is just to teach you kind of the simplest possible version of the technology, so that you can get an idea of what goes on.
Okay, thank you.
Okay. All right. Well, if not, then that's all for today, and I'll see you next time. Bye, everyone. Thank you for attending.